I'd ask you, first of all, let's start at the end rather than the beginning. What is the greatest thing, if everything went fantastically well, what would be the greatest outcome of the experiment that you're doing at CERN with the Hadron Collider?
Well, look around here. Look around at this fantastic landscape, or in the night, look up to the stars. All what we see is nearly 5% of the matter and energy of the universe. 5%. It took us roughly 50 years, 5 decades, to describe that, to understand it. And we haven't fully understood it yet. 95% of the universe are dark. 1/4 is dark matter, 3/4 is dark energy. And the greatest thing I'm really hoping is that the Large Hadron Collider will shed the first light into this dark universe. And this would not be a quantum jump. This would be a huge jump. This would be fantastic. I mean, in a few years, we could maybe write the early universe, the development of the early universe in a different way.
Well, we've done precious little with the 5% we know about it. Wouldn't it be a good idea to deal with that first?
But we also deal with this, of course. But I mean,
do you want to deal with it because you think out there are solutions to some of our problems, or you want to deal with it simply because you want to know what it is, or you want to deal with it because you're rather frightened of it?
Oh, I'm certainly not frightened of it. But the first thing which drives us is to gain knowledge. Yeah? And if you gain knowledge, you can use this knowledge in order to solve problems later. Yeah? Take as an example, it's now, I think, 83 years ago, that a theorist, a particle physics theorist, was brave enough to introduce antimatter. That is 83 years ago. It was a theoretical construct.
Right, before you go any further, let's just deal with antimatter.
No. Let me just say that today you use that in the hospitals.
Antimatter?
Yes. You didn't know that?
I didn't.
Okay. PET, positron emission tomography, uses the positrons. And the positron is the antimatter to the electron, which is part of the atoms. So 80 years ago it was pure basic science. Today we use it in the hospital.
PET, right, okay. Antimatter used in the hospital for what?
Oh, for scanning, for finding cancers, for example, etc. And then you can also treat the cancer with accelerators, for example.
Right.
With particles from accelerators.
Okay, so finding the dark universe, shining a light into the dark universe. What about something that most people here, I would think, would yearn for, which would be some completely non-destructive energy source?
That's not so easy. You see here.
You are creating energy
explosions
underground, and you're bombarding.
Yes. But we are creating this energy out of energy which we take from somewhere else.
So you use as much energy
as we create afterwards. But
you see, what I'm just thinking about is that if you look at the outcome, you have to look at the income, the money. And some politician somewhere, 17 years ago or longer, said, yes, we'll give you 6 billion euros, you can dig a very deep hole, you can have a lot of fun down there, and at the end of it, we're going to be able to see the dark universe. Now that, to a politician, is a very difficult thing. A, it's going to be beyond his electoral cycle, right? That's a big thing for any politician, to commit themselves to something beyond an electoral cycle, and secondly, something of such value to mankind that his great-great-grandchildren will look back and say, my great-great-grandfather committed himself to this expenditure because... So how do we persuade? Because you were in it, really.
Well, if you have a good project, if you have good arguments that you want to push back the frontiers of knowledge, you can convince even politicians. You can convince even politicians that, look, if we stop pushing back the frontiers of knowledge, then I think at some stage we give up to be humans. Yeah? I mean, if we do that, I have a very blunt example. I mean, you need to do basic science and applied science at the same time. I don't think you should distinguish between the two. Because if you stop basic science, at some stage you don't have the basis to apply for applied science. And just a very blunt example, applied science on a candle, it will never give you a light bulb. That's impossible. You need basic science on electricity. And then afterwards, applied science to use the electricity to make light. Yeah? And I remember very well the quote from Faraday. He was asked the same questions. What is this? He was working on electricity. What is this thing used for? What can I use that for? And he was asked by his minister.
Well, he knew what he was going to use it for.
His answer was, I don't know. But maybe one day you can tax it.
What they wanted to do was to build the circumstances in which you could do what?
The circumstances within which you can do two things. First of all, you can look into the old question of Faust, the famous book from Goethe, to discover what the world is consisting of and what it holds together. This is one thing. You want to go as deep as possible into the microcosm. And at the same time, you want to understand how the early universe developed. And we come very, very close to the Big Bang. We come as close as 1/1,000,000th of a millionth of a second close to the Big Bang. With our big accelerator, which is nothing else than a super microscope. It is the most powerful microscope in the world.
But you're dealing with facts. I thought the Big Bang was a theory.
We want to transform the theory into a fact, which will not be possible. We come only closer and closer to the Big Bang. We want to create facts. Once you extrapolate these facts, can support or falsify that theory. But everything we are doing at the moment looks like a Big Bang is something which happened.
And what do you do? What is going on there?
It's very easy. We take a bottle of hydrogen gas. There are atoms of hydrogen in. Now, how do you accelerate them? Now, you know, if you have a positive and a negative, how do you call it? The field between a positive and a negative part, then from the positive part, the positive particle is repulsed and attracted by the negative one. Mm-hmm. And once it goes to the negative one, you switch the field, then this is positive, it repulses it again, and it moves to the next negative one. So in that sense, you accelerate it like a wave. Like if you have a child on a, what is it?
Swing.
On a swing. If you push the child in the right moment, it gets accelerated. Okay? We do the same thing. If we are giving it the impulse at the wrong moment, the child stops or we lose the beat.
Just by using negative and positive.
Yes, it's just
reversing the flow.
Yes, yes. But that you do all around the ring.
Right.
And then, in order to keep the thing in the ring, you have a magnet which keeps the thing in the ring. Mm-hmm. And so you let it go. And at 4 places you collide these protons. And we have thousands of packets of these protons. Whereas then we say 10 to the 11 is 100 billion of the protons are in there, and then you collide them at 4 points where you have huge digital cameras, so to speak.
Are you effectively swinging the child all the time, more
yes.
and more and more and more?
No, we swing it up to a moment where we can no longer hold it. I mean, if you go to tracks and fields and you throw the hammer,
yeah.
If you turn around, it's faster and faster. At a certain stage, you can no longer hold it. So we only can accelerate the protons up to a moment until we still can hold them. Otherwise, we lose them again.
So when will you achieve the experiment?
Well, this is an experiment which goes on for 20 years. Yes.
So, I mean,
that's you see.
Before it's finished.
Yeah, but that doesn't matter. There are young people. There are many young people over there. I don't know. I mean, we are nothing else than a big scientific institution like a big university. Per year, with this big instrument, we have around 1,000 fresh PhDs. 1,000 fresh PhDs per year, roughly.
Particle physicists?
No. Yes and no. Of course they learn particle physics, but a particle physicist learns a lot. He or she learns a lot about innovative technologies. After all, this 27 kilometers, if I get sidetracked to stop me, this 27 kilometers ring is colder than the outer space. We are at 1.9 degree above absolute zero. The outer space is 2.7.
How do we manage to get down there?
Well, liquid helium. You need a lot of technology to do that. You need to create a vacuum in which these protons are running, because if it would run in normal air, they would interact with air, disappear.
It seems to me you've got all dressed up, you've got all the people, they're all young enough to live to see the end of the experiment.
But we get young people every year. So
okay, but you keep replenishing them so that they remain young enough. You have a very, very cold place.
Yeah.
You have an action in play that is limited to the point at which you don't want to let go of it.
Yeah.
Right?
Yeah.
What is it going to do?
Well,
what is it? What's in there?
What's in there? What's happening there? I mean, it's at the, as I told you, it's the coldest place. At the same time, it's the hottest place in the universe. Because, I mean, what you do when you collide these photons, macroscopically, it's nothing. That's a mosquito in full flight hitting another mosquito.
Conceptually, I mean, you told me about the hottest place and the coldest place. At any one moment, I stand in one particular place, am I very hot or very cold?
You're normal. No, the cold place we need in order to create enough strength for to hold the
So is that on the outer rim?
No, I mean the tunnel is filled with blue pieces with a lot of cryostars. It's nothing like a big refrigerator, which is inside that tunnel. But there's a magnetic field inside, and you have to cool that, and this you have to do with liquid.
So where is the heat? In the magnetic field?
There is essentially no heat because it's superconducting.
You said it's the hottest place in the world.
The hottest place in the world is in the collision.
The collision.
In the collision, yeah. As I said, macroscopically you collide two mosquitoes.
And these collisions are happening millions of times a second? Or?
Yes, at the moment with roughly 20 million times per second.
And this is going to go on and on and on for 20 years.
Yes.
And at the end?
No, all the time.
Yeah.
All the time there are results.
There are results.
Yeah, all the time results.
Like what? What is the result?
You give me 1 minute to explain that. In the first year of the running, we have only this small part of the meadow. Now all these physicists, the young students, they look for different types of plants in the meadow. One guy looks for grass, the other guy looks for a normal blossom,
buttercups
or whatever. And some guys look for four-leaf clover, for example. Now the guy who looks for normal grass, he doesn't need a lot of running time of this machine. For him, a small piece of this grass is enough. But everybody looks at the same time on all the grass which is available. So results are coming out all the time, depending on what you are looking for. If you are lucky, you look for something which you see immediately. If you are unlucky, like the four-leaf clover, you look 20 years until you have covered the whole meadow, you don't find anything, so you only set a limit.
So do you keep a few people who are not looking for anything at all, and are therefore open to seeing something nobody ever expected to see?
Oh, we have enough people who are looking very openly into things. Very creative, so sometimes I have to stop them.
I'm sort of getting there, but you see, I know in a moment that something dreadful will pass my lips. And that will be Higgs boson. Well, because actually, all I did to prepare for this, because I'm a dead loss, was to Google the Hadron Collider. You can't go 10 seconds into the Hadron Collider without meeting
the Higgs boson. Yeah.
And it seems to me that we would be letting ourselves down if we didn't address Higgs boson, because one result you are definitely going to have, well, as definite as any scientist dares to be, is that at the end of this year, is the next year, you will prove whether there is or is not a very, very, very tiny particle, which I think is the Higgs boson.
Yeah.
So, what is it, and why do you want to find it? And if you don't find it, does it mean it doesn't exist?
Yes, to some extent. You see, we know the Higgs boson, by the way, is named after the theorist Peter Higgs, Scottish theorist. And if you find it, he will get the Nobel Prize, and we have to hurry up. He's 80. But the point is, we know everything about this Higgs boson. We know all its properties. The only thing we don't know is if it exists. So, why do we look for it? Because 30 years ago, there were famous physicists who got the Nobel Prize for a fantastic model, the so-called standard model of particle physics, which describes these 5% of the visible universe. It has only one slight problem. It only works for massless particles. No, all the particles have mass. Okay, so something else must be there. So Peter Higgs plus some colleagues, they introduced a different mathematical formalism. And once you plug these two formalisms into each other, then the whole thing is a package which works for massive particles. Fantastic.
Well, let's just go back to mass. You're looking for something which gives particles mass.
Elementary particles, yes.
How do you give a particle mass? You mean, what is the mass of a particle? Is it its shape, its size?
It's neither shape nor size. For you, it's
an artistic question.
It's more like a weight, so to speak, a weight. The most massive elementary particle, which is today what was 100 years ago the atomos, the undivisible, is today an elementary particle which is essentially point-like but as heavy as a gold atom.
If you find Higgs boson and you can split it.
No, we cannot.
Well, why not?
Okay, let's just find it.
Well, look, we thought the atom was the smallest thing.
Yeah, but that's a long time ago.
Yeah, but then we split it and we made an unfortunately imperfect energy.
Well, that was the splitting of the nucleus, not of the atom.
Okay.
100 years ago, Rutherford found out that you are essentially empty. We are all essentially empty. Because the atoms, they are essentially empty space. It's just the forces between the electrons which surround the nucleus. It's these forces which make your body and your weight essentially here. The nucleus is a tiny, tiny part of the whole atom. And that was the start of the nuclear physics, and that's 100 years ago.
And what I'm suggesting to you is that if you discover at the end of next year something we will all live to see, the end of next year, you discover Higgs boson exists. Does it then, if it does exist, and you know all about its properties even though you don't know it exists, but does it mean that we might have the potential of discovering it too has some kind of a nucleus within it, and is splittable, and a deliverer of perfect energy?
Well, for the first thing, we would need an even more powerful microscope.
Oh no, not another 27 kilometers.
No, it would be another 40.
Who's counting these? That's big for 27 kilometers. There seems to be 40 is academic.
Yeah, exactly. What you have to do is you have to do new methods to find new methods in order to give more energy per unit.
I'm very serious. Yeah. I mean, if this now, I begin now to see what you're up to.
Yeah.
You're up to finding something which could not only explain antimatter and dark universe and the rest of it, but do much more than that. Provide us with some kind of future.
Of course. I mean, basic science like this is our future.
But then why didn't you sit there when I first asked you and suggested, well, what is the greatest thing you could find? The greatest thing you could find would be that this Higgs boson particle does exist and does have potential.
Well, because I'm a very cautious guy still. and I'm not sure what potential it really has. I'm not imaginative enough to find to stick out my neck there.
If you
and you see, as a director general,
conference,
I have to be very careful because I read it tomorrow in the newspaper.
Yeah. No, I'm going to tweet it as soon as the show. If you call a news conference, I hope you give us warning so we can come to hear your announcement, whichever way it is. I'm still young enough to be there at the end of next year.
You get invited, personally.
But hang on a minute. I mean, if you stand up and say, I'm really terribly sorry, we know all about its properties, we know everything there is to know about it, but I'm awfully sorry not to tell you it doesn't exist.
That would be great.
Would it?
Yeah.
Why?
Because then we find something else.
You mean because there is something else?
There is something else.
Yes.
Definitely. I stick out my neck. If it's not the Higgs, which is the most plausible explanation, then it must be something else.
Then these properties that you know about are the properties of something. They are not necessarily the properties of Higgs boson.
Right. There must be something else which fulfills the job of the Higgs boson.
Will it mean you have to completely change tack?
I have to
completely change your direction?
Not the direction. I mean, it must be in the data which we collect. Then we have just to be open enough to find it, and the people are open enough to find it. They look essentially for everything they can think of to find it. And the point is that you know what the thing has to do then, but it could look different to the Higgs boson. But then we have to rewrite even our knowledge of the 5% of the visibility, a little bit at least.
Now you've set 20 years. You just stuck a pin on a number, or you think 20 years will give you the time you need
20 years, I think,
to resolve whose properties you're looking at?
It's a sort of experience one has. I mean, and what you learn, you know you might be able to use it at some time, but you don't know when, and you don't know from what.
I remember being a correspondent in Washington and attending a news conference given by Ronald Reagan, when another space program got up, and he talked about the great spin-off of Teflon, sorceries. It's funny to hear an American president talking about sorceries.
Well, he needs such a kind of
when you're working, are you able to talk about spin-offs that perhaps are about CT imaging or...
Well, who is not using the World Wide Web? The World Wide Web. Who is not using it?
The World Wide Web.
The World Wide Web.
Right. Who's not on the internet?
Okay. 5, 1, 2, 3. 3 per minute. The World Wide Web. 3 per thousand. The World Wide Web was born at CERN. And it was born, and that's a message to the young people, not with the Big Bang. It was born 1989. Why? Because at that time our experiments became so international that we needed a software platform which guaranteed immediate access, reliable access for all the scientists contributing to the experiments.
Was Tim Berners-Lee there in
Yes.
In CERN?
Yes. Yes.
Really?
And you can imagine http:// that can only come from physics. Now we needed it at that time. This is a byproduct. And we have his next computer in an exhibition with us, and we are giving it on loan to the Royal Society, or to one big museum in London.
So Tim Berners-Lee was a part of the physicist?
Well, he was helping the party of physicists. He was in the IT sector, in the computing sector.
And in some way he was infected by what was going on at CERN.
Everybody who is at CERN is infected. It's a stimulating atmosphere, I can tell you.
How many people are actually there at any one time?
At any one time, I would guess between 6,000 and 8,000. Well, we have 3,000 people employed by CERN altogether, with including many postdocs, young people. And we have 10,000 scientific users from all over the world, who are not all the time there, but they come and go.
You know, as a newsman, I've only ever discussed CERN twice. Once when it opened, and once when it broke down.
Well, CERN didn't break down, the LHC broke down.
Yeah. It was rather central pump, so.
It was, yes.
What happened? What went wrong?
Well, fortunately, it was before my mandate. Okay. You see, you can, when you build a 27 kilometers new machine, you have never built such a machine before. Okay, so it's its own prototype. You can test all the components, but then you have to bring these components down into this tunnel, and then you have to connect them. And one of the 10,000 connectors was burning through. I mean, had a short circuit. It's easy to replace a light bulb once it had a short circuit, but you don't do it immediately afterwards because you burn your fingers. Yeah. You have to wait some time until it's cooled down. We had to wait until the thing was warming up. And that takes roughly 1 month to warm up the whole thing. And then we had to replace a lot of pieces because when you have a burning connection, in liquid helium, you can well imagine that liquid helium boils, and then of course it has a huge pressure and you have a collateral damage. So that had all to be replaced. And then of course we want to avoid such an incident again. That means we have introduced new measures in order to hopefully avoid something like this again, and that took a bit more than a year.
Because actually the original report suggested the thing was much more serious than that. That it might have much longer term.
Well, it has in that sense a longer term implication that I'm at present running the machine only at half its power, at half its energy, because I know the connections are safe for this energy. In order to go to full energy, I need another 1.5 years of repair, of fixation.
And then it can full speed.
And then it can run with full energy, with full speed.
So you can't carry out the full extent of your experimentation.
No, but that doesn't matter. We are now at an energy which is a factor 3.5 higher than ever attained by mankind, and this is enough for the Higgs boson.
You are producing 3.5 times more energy than mankind has ever produced.
No. We reach an energy level. Yeah. Okay. Which is much higher than any energy which was up to now achieved by accelerators. But the cosmic accelerator does much more.
You asked if there was anybody in here who did not worship on the World Wide Web. I'd like to ask how many scientists there are in here of any dimension at all. Good.
Oh my
that's really impressive. Wow. I mean, I can say definitely.
So I hope I didn't make any mistake.
15%, which I think is a very high showing in a literary professor.
Yeah.
Would anybody, you don't have to be a scientist, would anybody like to get the ball rolling on an interactive basis? Yes, the magazine up, and you can keep the magazine up, the microphone will come to you. Just down here, keep it up.